Good day, dear students. Today's topic is the refrigeration cycles. The refrigeration cycles is generally based on the reversible heat engine cycles. As we will be studying in the following minutes, the refrigeration cycles plays important role in the thermodynamics, in the heat transfer processes, and in power engineering, heat engineering generally. A major application area of thermodynamics is refrigeration, which is a transfer of heat from a lower temperature into a higher temperature one. Devices that produce refrigeration are called refrigerators, and the cycles on which they operate are called refrigerating cycles. The most frequently used refrigerating cycle is the vapor compression refrigerating cycle, in which the refrigerant is vaporized and condensed alternately and is compressed in the vapor phase. Another well-known refrigerating cycle and is the gas refrigerating cycle, in which the refrigerant remains in the gaseous phase throughout. Other refrigerating cycles discussed in this chapter are cascade refrigeration, where more than one refrigerating cycle is used, and absorption refrigeration, where the refrigerant is dissolved in a liquid before it is compressed. We all know from the experience that the heat flows in the direction of decreasing temperature, that is, from high temperature regions to low temperature ones. This heat transfer process occurs in nature without requiring any devices. The reverse process, however, cannot occur by itself. The transfer of heat from a low temperature region to a high temperature one requires special device called refrigerators. For example, in this picture we can see the refrigerating cycle. The refrigerating cycle works as the heat is absorbed by some heat transferring unit, then it's compressed, then the heat is transferred to the warm environment with the temperature higher than the environment. Then our body then goes through the process of the pressure dropping process. Same thing is with the cold environment and the house. The refrigerator are a cyclic device, and the working fluids used in refrigeration are called refrigerants. A refrigerator is shown schematically in figure 11.1a, where QL is the magnitude of the heat removed from the refrigerated space at temperature TL. QH is the magnitude of the heat rejected to warm space at temperature TH, and the W net is the network input to the refrigerator. As discussed in chapter 6, QL and QH represent magnitudes and thus are positive quantities. Another device that transfers heat from a low temperature medium to a high temperature one is the heat pump. Refrigerators and heat pumps are essentially the same devices. They differ in the objectives only. The objective of a refrigerator is to maintain the refrigerated space at low temperature by removing heat from it. Discharging this heat to a higher temperature medium is merely a necessary part of the operation, not the purpose. The objective of the heat pump, however, is to maintain a heated space at high temperature. This is accomplished by absorbing heat from a low temperature source, such as cold water or cold outside air in winter, and supplying this heat to a warmer medium, such as the house. The performance of the refrigerator and heat pumps is expressed in terms of coefficient of performance, defined as the following: desired output, required output; cooling effect, work input. Or if we are talking about heat pumps, the heating effect, work input. These relations can also be expressed in the rate of form by replacing the quantities QL, QH, and W net by QL, QH, and W net in respectively. Notice that the Q of R and Q of HP can be greater than 1. The cooling capacity of the refrigerator system, that is, the rate of heat removal from the refrigerated space, is often expressed in tones of refrigeration. The capacity of a refrigerating system that can freeze 1 ton of liquid water at 0 point degrees into ice at 0 point degrees is 24 hours is said to be 1 ton. 1 ton of refrigeration is equal to 211 kilojoules per minute or 200 BTUs per minute. The cooling load of a typical 200 square meters residence is the 3 ton range. The Carnot cycle is a totally reversible cycle that consists of two reversible isothermal and two isentropic processes. It has the maximum thermal efficiency for given temperature limits, and it serves as a standard against which actual power cycles can be compared. Since it is a reversible cycle, all four processes that comprise the Carnot cycle can be reversed. Reversing the cycle does not also reverse the direction of any heat and work interactions. The result is a cycle that operates in a counterclockwise direction on a TS diagram, which is called the reversed Carnot cycle. A refrigeration heat pump that operates on the reversed Carnot cycle is called Carnot refrigeration or Carnot heat pump. As you can see here, this is the reversed Carnot cycle. For example, how does it work? The refrigerant absorbs cold from a cold medium. Then, after the compressor, the cold medium has the higher temperature. Then, after going through some heated space, it loses its cool but stays with the high temperature. Then it goes to the turbine where the pressure drops and it liquefies. Then it goes to the condenser. Many of the impracticalities associated with the reverse Carnot cycle can be eliminated by vaporizing the refrigerant completely before it is compressed and by replacing the turbine with a throttling device, such as an expansion valve or capillary tube. The cycle that results is called the ideal vapor compression refrigeration cycle and is shown schematically on the TIAS diagram in figure 11.3. The vapor compression refrigeration cycle is the most widely used cycle for refrigeration, air conditioning system and heat pumps. It consists of four processes: isentropic compression in a compressor. As you can see here, the pressure goes out. Constant pressure heat rejection in the condenser here. Throttling in an expansion device, and the constant pressure heat absorption in an evaporator. Generally, that's the main ideas of the refrigeration cycles. Thank you very much for your attention.